I welcome all of you to the class. As far as today's class is concerned, in today's class, we'll be talking about the composite beams. In the previous classes, we were talking about the beams which were made of only one material. But today we'll be analyzing the beams which will be composed of more than one material. Beams which are made of more than one material are known as composite beams. As far as the mechanical engineering is concerned, in mechanical engineering, we often encounter the beams which are made of combination of more than two materials. If you look at the automobiles, in automobiles, the beams that we use, they are made of single material, like cast iron, for example, or the beams that we use in our household applications for making of the houses. They are all made of wood, but nowadays you often find the beams which are made of concrete. So you have two or more than two materials. You have RCC, reinforced concrete, steel or rods being inserted in the cement. Okay, so such a type of beams are known as composite beams. So from now onwards, we'll be talking about the analysis of the composite beams and the methods that are used for the calculation of their stress strain and their design procedures. As far as the uh, first stage is concerned, in the first stage, uh, we'll be having what's known as the introduction portion. Okay, now in the introduction portion, first of all, as is clear from the slide, composite beams combination of many materials. If you look here on the left hand side, we have a beam that is made of wood. Okay, so this portion is a wooden portion, but this wooden portion is having one portion at the bottom that is, say, for example, steel. Okay, so here we have this portion is wooden portion, this is wood, and if you look at the base, this is steel. Okay, so this beam will be subjected to the load, okay, or the bending moments, right? But if you look, this beam entirely is responsible for withstanding this entire load. Okay, and this beam itself is a combination of more than two materials. It's combination of wood, it's combination of steel. Sometimes we will be having a steel section followed by a wooden section, okay, and one more steel section. So we can have this is steel section, this is steel section, and this is wood. So what we can have a wooden section, wooden portion in between two steel sections. Okay, so that's also known as, so that's also an example of composite beams. And if you look at the right hand side, on the right hand side, we are having, as I was stating, you have a wooden portion. We're having a wooden portion, and reinforced in between these wooden portion is the metal portion. Okay, so this is also an example of what's known as the composite beams. So please be careful when we talk about the composite beams. We should not be confused with the composite material beams. Okay, there is a material by the name of composite materials. These are not composite material beams. Okay, these are composite beams because they are composed of more than one type of material, right? So we talk about these beams as the composite beams. Okay, now based on the composition, we can have a plastic core, and we can have, say, for example, we have a steel sections. We have two steel sections. In between two steel sections, we're having a plastic section. Okay, so this type of beam is a beam where we have a plastic section. Okay, we have placed a plastic section in between the two wooden. We have placed a plastic section in between the two uh, steel sections. Number one. And if you look at this portion, this is the portion where again we are having a structure. This is called a honeycomb core. We're having a honeycomb core, okay, in between the two metal sections. Okay, so we're having a metal section here, we're having a metal section here, and in between a metal section, we're having one more material, and this material is in the form of a honeycomb. This is called a honeycomb core. And the third one is again, this is a metal portion, this is a metal portion. In between the metal portion, we're having what's known as a corrugated core. So this is a corrugated core. So if you look at the entire applications, if you see, we can have a plastic portion in between the two steel portions. Okay, we can have a honeycomb core, or we can have a corrugated core. So these are examples of what are known as the composite beams. As we can clearly see that in these beams, it's not a single material beam, it is combination of two or more than two types of materials. Okay, this is what we call as a composite beam. Now let's do the analysis portion of the composites. So when we talk about the analysis, we have to calculate the stresses and strains in the beam. We have to do the analysis, what we know as the calculation of the stresses and strains in the beam. So how do we do the analysis? In order to do the analysis of the composite beams, what we first of all we take a beam section. Let's suppose we are having a beam. This is a beam, and this beam is composed of two sections, as you have section 1 and section 2. So we can say this is material 1, this is our material 1, and this section 2 is our material 2. So we are having two materials. We are having material 1 and we are having material 2. Right? Now, if you look, this material 1 and this material 2, let's suppose this is the cross section of the beam, for example. Okay, we can do this analysis for this type of cross section, then we can we can do it, we can apply this analysis for other types of cross sections. Okay, so this cross section I'm taking over here, fine. And look at this cross section. You are having material 1 here, you are having material 2 here, and this line is the plane which is the intersecting plane. Okay, the common plane between section 1 and section 2. Okay, as is over here. So we are having material 1 over here, material 2 here. In between the two materials, we are having one more, we are having a common plane. Okay, we are having a common section, right? So this common section is very important for us, fine. Look at this point O as well. This point O is the origin of our coordinate system. This is the origin of our coordinate system. Important thing in the analysis is, as we were talking about the simple beams, as we had a beam, and this beam if subjected to bending, okay, and if you take the cross section of this beam, say for example this is a rectangular cross section beam, then essentially we know that there is a particular plane of this beam which is known as a neutral plane. This we have done in Mo 1. This is called the neutral plane, and its projection is called neutral axis. Let me call this as a neutral plane. Neutral plane is a plane where the beam neither undergoes compression, where we have neither compression, nor tension. The beam undergoes nothing. Okay, because when the beam is subjected to bending, as the beam bends, okay, so upper portion of the beam is under compression, the upper portion of the beam compresses, and the lower portion of the beam is under tension. Okay, so if you look here, you are having tension means you are having positive stress, compression means you are having a negative stress. Okay, so you are having a physical quantity changing its sign from plus to minus, so definitely it must pass through a point where the value of the sigma will be equal to 0. Okay, so that line or that very plane is what we call as a neutral plane, right? Now if you look at the composite beams, in a composite beam, okay, as far as this type of beam was concerned, which was isotropic, composed of single material, when we had an isotropic beam which was composed of a single material, then we know its neutral axis was passing through its centroid. Okay, its neutral axis was passing through its centroid. We know this was the case for a type of beam which was isotropic. Okay, the neutral axis was passing through the centroid, but here that's not the case. The neutral axis here does not pass through the centroid, because you are having material 1 here, you are having material 2 here. Okay, let's assume that we are having this axis, this z axis, this is our neutral axis. Let's assume this to be our neutral axis. This is an assumption. Okay, let's assume this axis to be our neutral axis. Okay, and let's assume that this point is the centroidal point of this beam. Fine. But the fact is, here we are taking neutral axis away from the centroidal axis, because passing of neutral axis through the centroidal axis is good for isotropic materials, but that is not the case for non-isotropic materials. Okay, we are having a non-isotropic material. It's a composite beam. So we assume that the neutral axis is passing through the axis O, okay, and the centroidal axis is somewhere over here. Now, from the earlier analysis, we already know the equation. We know the strain in the beam, strain along x-axis, strain in the beam in bending is equal minus y by rho, where this y is the distance from the neutral axis. This y is distance from the neutral axis. Okay, where this y is the distance from the neutral axis. So we write eta x is equal minus y by rho. Okay. Now, very important is that this 1 by rho is also written as kappa, what we call as a curvature. So we have ky, where k is known as the curvature of the beam. K we call as the beam curvature. We have done this in mechanics of materials. In the earlier courses, we know eta x is equal to minus k into y. Now, when we apply, this is our neutral axis. So all the distances in from the neutral axis upwards are taken as positive y, and all the distances from the neutral axis in downward direction is taken as negative y. Okay, so if you look here, if you are going upwards, so your y is positive, so our y is positive, therefore strain will be negative. That's why the strain has been drawn along negative x-axis. Fine, so the strain is along negative x-axis, and this strain will attain the maximum value when the y will have maximum value. That's at the top surface. Okay, at the top surface the strain is maximum, and strain at top surface is written as eta A is equal minus k into y A. Okay, the distance from the neutral axis to this very point, that's what we call as y of A. Okay, now from the neutral axis in the downward direction, the value of y is negative. When the value of y is negative, then then eta x becomes equal ky, it is positive. Okay, therefore the strain in this direction, from in a direction downwards from the neutral axis, will be positive. Okay, and the value at this very point, at the point B or on the surface B, it will be eta B is equal kappa times y of B, where yb is the distance from the neutral axis. Okay, and here at the neutral axis, the value of the strain has to be equal to 0, because we know the neutral axis is an axis where the stress is 0, where the strain is 0, where the beam undergoes nothing. Okay, so this is the point where the beam, this is the point where this axis is the neutral axis, and the value of the strain on the neutral axis is 0. Number one. Number two, in the analysis is in this diagram, is this diagram has been drawn with the help of this formula, as we already know this formula. The important thing about this formula is that if you look at this common surface, if you look at the interface, the common surface between section 1 and section 2, that is the common surface between material 1 and material 2. If you look at the common surface between material 1 and material 2, that is this surface. Okay, at this very surface, the value of the strain is common. Okay, so it means the value of the strain on the centroidal axis, or the plane passing through the centroid, is same, that is eta c. The question is why. The why is because if you look at the beam is it's constrained, or we can say it is the surface is a common surface. Okay, it's a common surface between material 1 and material 2. Okay, so what will this common surface do? This common surface between material 1 and material 2 will undergo some value of the strain, but the value of the strain will be single. A material cannot have two values of the strain. Okay, so the strain at the surface, at the intersecting surface between material 1 and material 2 is same, that is eta c. Now, if you look at the values of the stress, if the material behaves as the linear material, if it obeys the Hooke's law, if the material is linearly elastic material, we should say, if the material is linearly elastic, okay, then the value of the stress sigma is equal to Young's modulus times the strain. Okay, Young's modulus times the strain. Now we are having material 1. Its Young's modulus of elasticity is eta 1, E1, and we are having material 2. Its Young's modulus of elasticity is E2. Okay, now we don't know what is maximum. Is E1? We can have cases. Case A can be E2 is greater than E1, or case B can be E2 is less than E1. But E2 cannot be equal to E1. Okay. If E2 is equal to E2, then the material is isotropic, which we do not want. Okay. Which we have already analyzed. We don't want this. We can have a case either E2 is greater than E1 or E2 is less than E1. Let's assume for some time, let's take this assumption into consideration. Let's assume that E2 is greater than E1. Then what will be the value of the stress in the material 1? Okay. The value of the stress in material 1 will then be the value of the stress in material 1 will be sigma 1 is equal to Young's modulus of elasticity of material 1, that is E1, and strain in material 1, that is eta in material 1. Fine, eta in material 1. Okay, or eta in material 2. Similarly, we write sigma 2 will be equal to E2 and strain in material 2. This equation can further be modified as, this can be written as E1, and eta 1 can be written as minus K Y, and this can be written as E2 minus Ky. Okay, Y is the distance measured from the neutral axis. Right? Now we are assuming E2 is greater than E1. And if you look at this Young's modulus of elasticity, we define Young's modulus of elasticity as stress divided by strain. Okay. If we are having two materials, for that materials, E2 is equal to sigma 2 by eta 2. Okay. And for another material, E1 is equal to sigma 1 by eta 1. And we have already made the assumption eta E2 is greater than E1, then sigma 2 by eta 2 will be greater than sigma 1 by eta 1. Okay, sigma 2 by E2 will be, that is okay. Okay, then that gives us an information about this, that sigma 2 has to be less than sigma 1. There's a reason for it, because we are having an inverse relation. If the value of E is inversely proportional to eta for the same value of sigma. Okay, so if E2 of a material is greater than E1 of another material for the same value of stress, then it's quite surprising. Say, for example, the definition is, we write E2, E is equal sigma divided by eta. So we define E as the amount of stress required to produce unit strain in a material. Okay, so to produce unit strain in a material, the amount of stress required. Okay, so when we are having E2 greater than E1, it means amount of stress required to produce unit strain in material 2 is more than the amount of stress required to produce unit strain in material 1. Okay, it's like this. Okay, fine. So if you plot these values of stress, then the value of the stress, since sigma is equal to E times strain varies linearly. Therefore, this value of the sigma also varies linearly. Okay, this is when we measure from the neutral axis. When we measure the stress, since this eta is negative, therefore stress will also be negative. It has been drawn like this. Fine, it has been drawn like this. Okay, In the same way, so if you look at this contact surface, this is sigma 1 at C. Just have a look of this diagram. This is very amazing diagram. If you look at this diagram, if you look at this common interface, common surface between the two beams, the value of the stress as measured from this formula will be equal sigma 1 or sigma A at point C is equal to something, okay? That is here. Now we are having to calculate sigma in material 2, we'll use sigma 2 is equal to E2 and strain in material 2. So E2 varies linearly, therefore sigma 2 also varies linearly because E2 is constant. Therefore, as we go from neutral axis downwards, okay, this stress value will be positive, fine. But look at this portion, this portion belongs to what? This portion belongs to material 2, not to material 1. So in order to calculate the stress on this very surface, let's use the formula sigma 2 formula. Okay. Therefore, when we use the sigma 2 formula, because this portion is a common portion, when we use the sigma 2 formula, therefore the stress at the common surface comes out to be equal sigma 2c. When we use the formula for the material 2, when we use formula for material 1, that is sigma 1 is equal to E1 eta in material 1. Okay. Therefore, what will happen? The value of the strain at the common surface will be sigma c because of the formula 1. That is over here. That is this much. Okay, if you look, you're having two values of the stress. One value of the stress is because of this formula. Another value of stress is because of this formula, but the strains will be same. So the value of the stress at the normal surface, at the common surface are different, but the values of the strain will be same. Okay, we'll talk more about it once we will be doing the analysis of the beam. So first of all, important is the location of the neutral axis. How do we locate the neutral axis? Okay, so we locate the neutral axis as this. Some very relevant information is in this slide. That is sigma x1 is given by this formula as I was just discussing, and sigma x2 is given by this formula. Fine. If you look at the neutral axis does not pass through the centroidal axis. The values of the stresses are different at the common interface, but the values of the strain are same at the contact surface. So at the contact surface, we are having the same values of the strain, but at the contact surface, we are having different values of the stress. And very important in composite beams is that the neutral axis does not pass through the centroidal axis. In the overall analysis of these beams is, first of all, the location of the neutral axis. Without the location of the neutral axis, the analysis cannot be performed. So first of all, we should first locate the neutral axis. Just as I was stating that neutral axis is an axis, that the neutral axis is an axis on which the value of the force is equal to 0. The value of the stresses is equal to 0. The resultant strain is also equal to 0. Okay. So if this axis happens to be the neutral axis, if this is a neutral axis, for example, let's take a small area element across it. Okay. This area element is like this. So you are having a beam portion essentially like this. This is the beam. Fine. And this is a section out of it. There's a sectional view of this beam. Fine. So if you look at this section, so you'll be having some value of stress here, sigma, okay, somewhere compressive, somewhere tensile. So on this small area dA, the value of the force acting will be sigma dA. Sigma is the resultant stress, okay, because of two sections. Now you are having material 1, material 2, okay. Therefore, what will be the resultant force on the entire material? The resultant force on the entire material will be integral of sigma dA. Fine. But if you look at sigma dA, area is area, okay, but this stress is composed of two materials. So you are having on a portion of this area, you will be having sigma x because of material 1, and here you will be having sigma x because of material 2. Therefore, we can write this as, this is integral Sigma can be written as combination of two stresses, sigma 1 and sigma x1 and sigma x2, and you have dA. That's here. So if you open up this integral, sigma x1 dA, sigma x2 dA, but this integral is taken over an area which belongs to material 1, and this integral is taken over an area which belongs to material 2. So the resultant stress is equal 0. Resultant force, this is sigma into area, that is force. So apply the formula, sigma x1 is equal to E1 K into Y dA minus E2 ky dA taken over an area element for material 2 has to be equal 0. Therefore, this formula we obtain, this is the formula that we use for calculating or locating the neutral axis. Let me repeat it. How do we use this formula for the location of the neutral axis? We essentially have a beam portion like this. We have a beam like this. Okay. So on any section of the beam, we'll be having stress values. So we'll be having, this is on the top portion, we'll be having the compressive stresses. We'll be having compressive stress like this. We'll be having compressive stress. And on the lower portion, we'll be having the tensile stress. Okay. So if you look at this area, total area of cross section, if you look at the total area of cross section, the total area of cross section is, the total area of cross section here is dA. Okay. But when you take this dA like this dA will be combination of two materials, area of material 1 and area of the material 2. So on material 1, you are having sigma x1 on area element for material 1. On portion 2, you are having stress sigma x2 on material 2. So you will write integral sigma dA is the total force, and this has to be equal to 0. But this total force is the combination of two forces, stress sigma x1 in material 1 and area of material 1. We write it like this, plus stress in material 2 multiplied by area element of material 2. This has to be equal to 0. Apply the formula. We get sigma I YdA plus E2 YdA has to be equal to 0. If we further process this equation, we can write this as, just a minute, we can further write this. If you look at this YdA, we know this is also written as the this is known as what we call as the moment of inertia. Okay, this is a moment of inertia terms. We can also write it in terms of the moment of inertia. But right now we can at least recall and memorize that this is what we use for the calculation of the neutral axis. So in the analysis of the composite beams, the first and foremost step that is to be taken is the location of the neutral axis. We'll continue from it in the next class.